Conservancy. I think many of you know who we are, but just in case you don't, I will just reiterate we're the Land Conservancy for Kingston, Frontenac, Lennox, and Addington. We're all volunteer group, a registered charity. We're currently protecting 15 properties, and we've now got 490 hectares or just over 1,200 acres. And our goal as land trust is to provide permanent safe havens for nature. I'm going to introduce our speaker, David Kerr. David is a geological engineer who has recently retired and is now living in the Kingston area, and is learning about the geology of Kingston area. So I will pass this to you, David, and if you want to say anything more about yourself, please go ahead.
Okay, right. Well, thanks very much, Mary Alice. I'm delighted to be here. The Kingston area is really my home, although I haven't done that much work around here. I'm certainly looking forward to learning more about the geology of our near environs. For those of you who don't know me, my professional background is as a geological engineer and involved in mineral exploration. So for most of my career, I was engaged in by mining companies to help understand the genesis and the structure of their ore bodies. These would be ore bodies of copper, zinc, tin, nickel, gold, that sort of thing. As I say, I'm retired now, but I can't escape my love of rocks and my fascination with the processes that form them. So I'm looking forward to spending a lot more time out in the field around here. My daughter Ailsa and we love to go for hikes in the woods. I mean, whenever we heed the call or need to ground ourselves in the natural world. She's an urban farmer and a biologist and a tree lover. And because I'm a geologist, we find that our discussion on the trail almost inevitably touches on the intersection of these two natural sciences. And I hope that's the direction we're going to go with this talk today. That's the aim of the presentation, and I hope I found a reasonable balance between informative without being too technical. And I'm looking forward to the discussion at the end. And thanks to everybody who sent in photographs. So, I think I'm ready to share my screen.
Do I have to do I have to stop sharing, Mark?
Yeah, you stop sharing yours and then David can
Okay, it's
take over.
stopped.
Okay. Okay.
Don't you touch that.
Okay. I just got to get. Can other people see? I
Yes,
can. I've got to
you have
get
a
rid.
presentation mode.
Yeah. I'm trying to get out of seeing everybody else. Any ideas what I hit to do to get rid of that? I'm only seeing a bunch of faces.
Maybe you need to, oh, you're only seeing faces. We see your screen, but
Yeah.
it's not in presentation mode.
No, but I can't see my screen at all.
There's also a participant icon at the bottom. If you click on that, it might collapse that.
Okay. Oh, sorry about this, folks.
At the top right, I have a view icon.
Yes, that's what I'm playing with right now.
Okay.
And I don't want to see me. I want to see Mike. Oh, we're getting there somewhere now. I'm getting this message about multiple sharers. Okay. You
Someone
can
in the
all see my
chat,
screen,
Yes.
someone
right?
in the chat is suggesting you click on from the beginning, which is at the top left
Yeah.
above your slides. I think that might help. You're not in slide
Oh,
mode.
there we are. Okay, finally I got to my screen, which is what I needed to be in the first place.
Great.
I can't see. What is that? Do I see anything?
No, I'm seeing, this is weird. I'm seeing my screen, but it's not reacting to me. It's like I'm seeing somebody else's version of my screen.
Oh,
I'm going to stop sharing and start all over again.
Probably a good idea.
okay.
Mm, it's really good, and I'm hungry.
Hmm. How do I get rid of everybody who's watching? Because I can't.
Can you see your,
Ah, we're getting close.
How about taking it off gallery?
One possible issue is that when oh,
Decrease
Okay.
your Zoom screen. Decrease your Zoom screen and click on your Bedrock of Life Geology
there we
screen.
go.
There we go.
Yeah, yeah.
Here we are. I think this is going to work. Yes.
great.
Okay. Sorry about that, folks. I was just so excited to see how many people were on. I just didn't want to lose the sight of you. So, anyway, welcome to the talk, the Bedrock of Life, the geology of our region. Some of you will recognize the map that's in the upper right. It's actually a land conservancy map, and you're going to see this map or maps very much like it several times through the course of the presentation. It's a regional geological map, and really there are about 2 or 3 different domains. The brown area, the area colored brown on the map, is where the bedrock is composed of near horizontal sedimentary layers of limestone. And Kingston lies in that particular field. The multicolored and more complicated rocks to the northeast are where the bedrock is composed of the older, more deformed rocks of the Canadian Shield. But I think before we go any farther, I'm going to make sure that we've all got sort of Geology 101 under our belt. So we're just going to talk about these 4 basic geologic concepts. So what's the difference between an element, a mineral, and a rock? Well, elements are the fundamental substances. They're the 94 naturally occurring elements on the periodic table. Potassium, symbol K, atomic number 19, is an example of an element. Minerals are composed of elements, but they have a specific chemical composition and a specific crystal structure. Potassium feldspar, which it's a mineral. It's common in our area, and it's composed of potassium, aluminum, silicon, and oxygen in a specific ratio in a specific structure. And rocks are composed of minerals, usually composed of several minerals mixed together, but not in a specified proportion. Granite, for instance, is principally composed of potassium feldspar, but also quartz, plagioclase feldspar, and micas. It's a common rock in our area as well. And just as an aside, when people talk about critical minerals these days, they actually really mean critical elements. Potash is a mineral, but lithium and nickel and the rare earths, those are elements. They're not minerals. They never occur on their own in nature. They're always combined with other elements to form minerals. Remember high school? You remember the 3 classes of rocks you learned about? There are igneous rocks. Igneous rocks form from the cooling and crystallization of molten material or magma. If the magma erupts at the surface, we call them volcanic or extrusive rocks. But if the magma solidifies in the subsurface, then we call them plutonic or intrusive rocks. And basalt and granite are common varieties of igneous rock. Sedimentary rocks form when fragments of eroded rock or shelly material or chemical precipitates form layers or bedded deposits, almost always in an aqueous environment. And sandstone and limestone are common varieties of sedimentary rock and both present in the Kingston area. Metamorphic rocks are changed rocks. They're igneous or sedimentary rocks that have been substantively changed by heat, by pressure, and chemical reaction. The deep burial in the earth changes limestone to marble, for instance, and granite changes to gneiss. So those are the three basic rock types. This should be a somewhat familiar map as well. It's a map of the globe. You're looking at a whole bunch of tectonic plates. And in the upper left, there's a little cross-section through the earth from molten or semi-molten core to the rigid outer layer or crust of the earth that we call the lithosphere. The outer crust of the earth is divided into tectonic plates, and these plates move with respect to one another at roughly the rate that your fingernails grow, which seems slow to us, but is quite speedy by geological terms. And the tectonic plates have different thicknesses, they have different relative buoyancies, depending upon their bulk compositions and densities. The oceanic plates are denser than the continental plates. Incidentally, the colored dots on this map all indicate locations of earthquakes. Now, earthquakes occur at plate boundaries, most typically, because tectonic plates, they grind next to each other, or they crash into one another, or they tear themselves apart, or one submerges beneath another. And when two thick, low-density continental plates collide with each other, like we see in the middle of this diagram, then mountain chains are formed. And all these tectonic processes have been happening for nearly all of the Earth's 4.5 billion years of history. Except for the first few 100 million years, which is the dark brown box at the bottom of this chart. And that's when the Earth was simply too hot, was being bombarded by too many asteroids to achieve any sort of crustal stability to form tectonic plates. So that's kind of Geology 101, just a few review of the basics for those that don't remember high school that well. So let's return now to the actual geology of our region. This is a geological map of southern Ontario, and it's published by the Ontario Geological Survey. It's about time that this gets updated, but it's still a good map. Kingston is the red star, and there's obviously a lot of information on this map. But I think for our purposes today, or at least at this point in the presentation, just look at the main domains. And I've broken them out in a little inset map in the bottom right. The highly colored and very texturally complex rocks in the middle of the map correspond to a part of the Canadian Shield known as the Grenville Province. And the Frontenac Arch, which lies just northeast of Kingston, links this portion of the Grenville province with the Adirondacks, which are also part of the Grenville province. On either side of the Frontenac Arch are these two pale bluish domains that they really are the relatively undisturbed sequences of younger sedimentary rocks, which were brown, rather confusingly, on the first map that I showed you. Anyway, to explain to you how these three domains came about, I'm going to tell you a story. Well, a story in three parts. And it's a tale of high mountains, it's a tale of warm ocean basins, and of glacial ice. So, as I say, this story takes place in three parts, and here's where these parts show up on the geological timescale. Old mountains, middle-aged limestone basins, and very young glaciation. So let's start with part one of the story. And for this, we go back over 1 billion years, so about 1.1 billion years ago. In the middle of this map, you see there was a continent at that time called Laurentia. It's kind of a predecessor to North America. You'll recognize Hudson Bay in the middle of it there. Laurentia was amalgamated with other continental masses into a supercontinent that was called Rodinia. This is older than Pangaea, which is maybe the supercontinent you've heard about, more likely. Anyway, as these continental fragments came together and collided with one another, mountain belts were formed, or they're also called orogens. The Grenville orogen was the most extensive of these, and the mountains would have actually rivaled the Himalayas of today. These mountains would have been 10 kilometers high, with roots that extended to a crustal depth of maybe 40 kilometers in the earth.
Wow.
This is where the Grenville orogen rocks are found today. And you can see that our region, the yellow box, is pretty much smack dab in the middle of the best exposed portion of the Grenville orogen. Now, all manner of rocks would have been caught up in this cataclysmic mountain building event. The rocks would have been twisted and folded by tectonic forces. They would have been metamorphosed by tremendous heat and pressure. And even significant quantities of molten rock would have been generated by the heat. And these magma bodies, being less dense than the surrounding metamorphic rocks, would have risen in the crust, like a helium balloon rising through the air. And tremendous earthquakes would have occurred within the mountain belt as well. And many of these earthquakes would have been focused on the suture zones between bits and pieces of continental crust that have been amalgamated into the supercontinent. Returning now to this map, which I love. Mountains don't exist forever. They get built up and they get eroded. And so for the next 500 million years or so, the Great Grenville Mountains were progressively eroded away until only stumps, really the deepest roots of the mountains, remained. And they're present in our region. And the rocks that we see here are gneisses and partial melt rocks and marbles and quartzites and rock called an amphibolite, which is used to be a basalt before it was metamorphosed, and all sorts of different types of intrusive rocks like granites and diorites and gabbros and so on. They're all different colors on this map. So these rumps of the Grenville Mountains really are the stage for the second part of the story. This is just a close-up of that area. So we've now moved forward in geologic time to the Ordovician period. That's about 450 million years ago. Life on Earth had begun to proliferate. At least it had in the oceans. Life on land was still a little bit sparse. But thanks to continental drift associated with plate tectonics, the Kingston region was at this time quite happily ensconced in a warm equatorial position, and sea level had risen. So most of the Grenville rocks were now submerged beneath warm ocean basins. And all sorts of submarine plants and animals lived and died in these basins. And their skeletal remains, which were composed mostly of carbonate minerals like calcite, gradually accumulated on the seafloor. They were progressively buried beneath even more carbonate sediment and ultimately were turned into limestone. The photograph on the bottom right is a very typical shelly limestone from the Kingston area. So nowadays, these limestones are well exposed, both northeast and southwest of the Frontenac Arch. And so I've drawn a cross section on the purple line looking towards the northwest, and it's a cross section through the crust. And you can see the relationship between the older Grenville rocks in pink and the younger sedimentary rocks in various shades of blue and brown and yellow and so on. You can see that the sedimentary rocks are actually really just a skin, a relatively thin skin, lying on top of the Grenville rocks. So if we were to come back to Kingston in, say, 50 million years, we might find that there were no more limestones left in Kingston. It was only shield rocks that had been uncovered by erosion. Incidentally, we don't know for certain whether or not all of the Grenville rocks were submerged beneath these warm ocean basins where the limestones formed. We think, in fact, that the Frontenac Arch may have been a line, an archipelago of islands, at least, linking the Algonquin Park Highland area with the Adirondacks. I'll just show you a couple of field photographs. This is a rock cut on the 401 near Highway 15, and you can see quite clearly how the limestone beds, they're not quite flat, but they're close to flat. They're draped on top of the Grenville basement rocks, which are on the right. Here's another photograph. This is a famous exposure on Addington Road. There are 3 rocks here. You'll maybe recognize the limestones at the top of the outcrop. The rock at the base of the outcrop that's very difficult to see is, in fact, it's some of the Grenville rocks. It's a quartzite, which is a metamorphosed sandstone. But most notable in the middle is this boulder bed. And we think that this is possibly a preserved beach that was once on the shore of a Grenville-aged island in the Ordovician Sea. So this is a pretty clear evidence that we had at least some of the Grenville rocks popping their head above water. So all these rocks are very interesting, particularly if you're a geologist. But if you're a tree, say you're a tree growing in a land conservancy refuge, you're probably more interested in the soil above the bedrock. And that brings us to the third and the most recent part of the story. So right at the top of the geological timescale. So we've entered the Pleistocene Ice Age, roughly maybe 1 to 2 million years ago. And continental glaciers have moved south to eventually cover virtually all of Canada. The southward margin of the Laurentide ice sheet did in fact cover Kingston, and this ice sheet remained here until it only retreated northward about 12,000 years ago. The glaciers, as they moved across the land, they stripped away soil and rock, and these components would have been carried by meltwater down to glacial lakes beyond the nose of the glacier. And you see that in the upper left. After the glaciers retreated, they left behind all sorts of landforms, like till in the upper right, which is really just detritus that's strewn across the denuded landscape. Also things like drumlins and moraines. Moraines are sort of linear piles of detritus that accumulate at the nose or along the flanks of glaciers. Some of the best farmland in our area, bottom left, is underlain by flat-lying, very nutrient-rich, silty clay deposits that formed in glacial lakes. These are glacial lacustrine lakes. And those once extensive glacial lacustrine lakes are now shrunk down to be the Great Lakes that we know today. Pictured in the bottom right is an esker. Eskers are these really interesting, sinuous sand and gravel deposits that were left behind when they were deposited by subglacial rivers. But when the ice was gone, so was the river, and these stand as topographically high areas in the landscape, and they're prized by construction companies for their sand and gravel content. One last photograph of a glacial feature. These are glacial grooves, which are carved into the bedrock. The bottom of the ice sheet would have had all sorts of stones embedded in it, and it would have been like like emery paper or whatever. And so in our region, we can look at the glacial grooves, and they confirm that for us, the ice traveled from northeast to southwest across our region. And quite coincidentally, that's very nearly parallel to the sort of the grain of the fabric of the Grenville basement rocks. Okay, so now kind of just to round out the story, we return to my favorite image. This is a close-up of the Frontenac Arch area, the geological map of Ontario. And on this map, you see there's the stipple pattern in the middle. These are the very, very high-grade metamorphic rocks that were the deepest part of the roots of the Grenville Mountains. The light blue colors with the polka dots are marble. The red colors are granites or granite-like rocks, and then the darker yellow are quartzites for the most part. The green rocks used to be basalts. They're now metamorphosed into amphibolites. Anyway, without getting into the details of this map, I could look at it all day. We really want to sort of think now about how the geology influences the biosphere. And this will sort of lead into our discussion in a minute or two. I mean, just like anywhere in the world, the elemental composition of the bedrock, as it weathers and breaks down, will naturally have an influence on the chemistry and the pH of the soil profile that's immediately above the bedrock. But in our cool climate, rocks weather very slowly. And the soils in our region are really quite juvenile because glaciation removed any mature soil profiles that we might have had just 10,000 years ago. But I find it fascinating how the distribution and nature of the Grenville basement rocks has clearly influenced the location and shapes of lakes in our region. So we're just going to look at this map, close up of this map side by side with a clearer lake map. And if you compare these two images, you'll see that Lobra Lake, which is this long, narrow, very straight, but very deep lake over here, corresponds very closely with a fault zone on this map, the geological map. There's a number of major fault zones on this map, not just Lobra Lake. There's a major one comes down from Charbot Lake all the way down to Verona. And you see, if you look over here, there are other lakes that are extremely narrow but straight. These also coincide with the location of these major crustal faults that they basically represented where continental components were collided with one another back in the Grenvillian origin. Then there are other lakes like Charleston Lake, Upper Rideau Lake here. This is Devil Lake here. And you can see that if you compare the distribution of the light blue marbles here in each of these three locations. You can see that basically the lakes are where the marble is, or where the marble was. It's now underwater because marble is the rock of our region that's most susceptible to erosion. It's subject to physical erosion, and it's subject to chemical erosion because it's composed of calcium carbonate and actually dissolves under acidic conditions. So it's kind of neat. If you're on a lake that's got an unusual arcuate form, chances are at the bottom of the lake, underneath the loon chip, of course, you would find marble. And if you're on a lake that's long and narrow and very, very straight, chances are you're on an ancient fault system that reaches deep into the crust. So anyway, I'm just going to stop there, and certainly open to questions.
Okay, if you have any questions, I haven't seen any questions go by in chat. So if you have any questions, maybe unmute yourself. Here's the first question for you, David. Gould Lake is very deep. Can you speak to that? Do you know where Gould Lake is?
Let's see. It's I can't find it on here, but there's Sydenham, so it's probably one of these up here, right?
That one,
That's Sydenham Lake there, I think.
yes. I think
Yeah. And that's
Gould
Knowlton
is-
Lake. So I think maybe that's Gould Lake, is it?
that looks from the right shape to me.
Yeah.
That looks the right.
No, I don't know why it's so deep, but most of the lakes are quite deep. There's a few that are a little shallower, when the lake is sitting on limestone. They tend to be more puddle-like. Um, but many of these lakes are exploiting very, very deep, uh, deeply eroded scars in the geological fabric. So their depth to width ratio is quite extreme. Yeah.
We've also got a question asking if you could tell us a little bit about the Frontenac axis or Frontenac arch.
Beyond what I've already said. Well, I mean, it's an unusual geological formation. It may be a product of just preferential erosion, if you will, but I rather suspect that it stands proud because it actually was a very, very resistant component of the Grenville arch, of the Grenville origin, resisted erosion particularly well, and has been basically has existed as a structure for nearly a billion years.
And we
It's
see that ecological connection that you spoke
absolutely,
about in the Adirondacks to Algonquin
yeah,
corridor
yeah.
stretch.
And I mean, it also makes for rather lousy farmland. So, um, the best farms are actually on the flat-lying rocks to the northwest, northeast, and southwest. So it has to some extent resisted development for that reason.
I worked at the National Park and Thousand Islands in another lifetime, and we used to see these images of the farmland sort of around the shield, in areas, as you
Yes.
say, that were flat.
Yeah.
I've got a question about the fault lines on the map, and someone asking if you can tell if earthquakes are likely in the future.
I'm going to just skip ahead a few here. I've got further on here. This is where I want to go to anyway. This is back to the whole map, so you can see the Frontenac Arch in context here. Follow my cursor here. This is a very, very major crustal suture. It's hundreds of kilometers long, and it doesn't seem to be active. It may be a wound that is currently healed, but you can see that even though this is a wound that's in the Grenville rocks, right? But the same fault continues on here. It's this blue line that carries all the way on here. So this fault was active back when when the Grenville origin was being assembled. This probably represented the contact between two different crustal components. But even after the limestones were deposited hundreds of millions of years later, following the erosion of the mountain, this fault must have moved again because it's cracked its way up into the overlying sedimentary rock. So it's not completely dormant, but more striking is this fault along the Ottawa River Valley. This is an active fault. And you can see that it's juxtaposing two very, very different geological domains. This domain here has moved down with respect to the rocks to the north. So when we get earthquakes, when you feel an earthquake in Kingston, it's likely a tremor associated with movement on this fault because it is an active fault. But it's not, as far as I can tell, a dangerous fault. It moves fairly often, and that's good. You don't want faults to get stuck and build up stress because then the resulting strain can be extreme. And it's not a deep-seated fault like we see along in Indonesia and so on, which can produce catastrophic effects. So, yeah.
Someone's asked about the rocks at Kingston Mills. Have you made it to Kingston Mills yet?
Yeah, that's interesting. Kingston Mills is where, let's see if I can go back a bit here. So Kingston Mills is just there. It's, there it is. And it's just where the limestones meet the shield. I don't think there's a great exposure of the actual contact there. But the reason that the locks are there is because you've got a crack that went through the basement rocks. A relatively minor fault, but it's one of many, many faults that sort of trend northeast, southwest. And that was enough for the waters to exploit, and that's why they've come across at that particular location. But it's a great place to put locks because you've got some nice tough rock on either side of your lock, better than in limestone.
Somebody's asked about the relationship generally between type of rock and vegetation. Like, is there a correlation with forests or forest types, that sort of thing?
You'd think there would be, and there is to some extent indirectly. For instance, if the rock determines where the lowland will be and therefore where the swamp will be, well, then the hemlock's likely to be there. But it's not necessarily there because of the composition of the rock. As I mentioned, rock weathering takes a long time here, and so there is to some extent local control over the local influence of the bedrock on the composition of the overlying soils, but I would suspect that most of the soils are still made up of leftover glacial till, as opposed to pieces of rock or indeed chemical constituents that would have come from the weathering bedrock. Yeah, it's a good question though.
Here's one I'd like to hear the answer to. Can you explain the role of plutons in the present surface structure?
Yeah, again, I'm going to go back to the other map. Oops, there we are. So the plutons are bodies of magma that rise through the crust, and as I say, they would rise. They're almost shaped like a helium balloon, actually, because they're rising. They're less dense typically than the rocks they're hosted by, so they rise up like blobs, like mushrooms coming out of the ground. So there's a lot of plutons visible on this map. If you look at all these orange-colored blobs that are numbered 44, these are all plutons of granite or granodiorite, which is a slightly more plagioclase-rich kind of granite. these will have risen up through the crust and they shoulder the other rocks to the side. So you see that the yellow and dark green rocks here that pre-existed the intrusion of these plutons are all kind of pushed aside and gathered into almost patterns that look like egg cartons, you know?
Yeah.
Yeah.
Somebody has asked, Joseph has asked, we are on Lowborough Lake and have been told it's really two separate lakes geologically. Southwest part being a cleft in the limestone, but the northeast being a typical shield lake with granite islands. Does that make sense?
It does make sense. Yeah.
Okay.
I unfortunately, Joe, Lowborough Lake doesn't show up on this map. I guess it's not wide enough to
Right, no.
justify a little strip of white, so it's a little hard to see where it lies. But I think I showed you back here roughly where it is. It's in that general vicinity there. So you've got quite a complexity of rock there. This is the southwest part here of Lowborough Lake, and that's where it's in limestone. And then you've got the northeast part here, which is up there. There's a fault that's not marked very well on the map, and I think you can see it. It's blue, comes down here like this. That's roughly equivalent to the lake. The lake, I'm tracing out the lake here, but you can't really see it very well. Yeah.
Yeah.
It's a fascinating lake, you know.
And they're somewhat, the two basins are somewhat different biologically as well.
Yeah, that's right. And there are some other really spectacular narrow lakes like this one up here. I think that's Canoe Lake. It's just a cut through
Yeah.
through the landscape. Yeah. Thanks for screening
Some-
all these questions.
Well, we'll take just a few more. We've still got to share some photos that participants have sent in. So maybe a couple more, but someone's asked generally about Holliford Crater. If you have any, do you know Holliford Crater?
I do. In fact, I
Excellent.
thought somebody might ask a question about it.
Excellent.
So there it is. This is really cool because this is about the only significant thing that happened between the erosion or during the erosion of the Grenville Mountains and the beginning of the deposition of the limestones. A meteor hit the Earth at Holliford about 550 million years ago. So an instantaneous event. So it would have crashed into the Grenville rocks. The limestones didn't exist yet at this point. But nevertheless, after the limestones covered this up, the ring fractures that are in the basement rocks propagated up into the overlying limestones. So you can see the crater, but what you're seeing actually is the upward projection of the crater, not the actual crater itself. I think it's quite fascinating that you can see this so well. It's hard to see when you're on the ground. It's just a sort of gentle depression. It really just looks like a circular swamp. Anyway, this is much smaller than the meteor that hit the Earth 65 million years ago and wiped out the dinosaurs. This was just a little guy. It's really quite amazing that record of this has lasted this long.
Highway 2, just near Fort Henry, south side of Fort Henry, just before the Highway 15. There's a dark horizontal band of rocks in the middle of the rock cut. And this can be seen in rock cuts around Kingston. And just wondering if you had any comments about
So this is a horizontal band that's not the bedding. Maybe I'll just go to the chat. I can sort of read that myself. Okay.
Yeah, it's from Ken and Diana.
Okay.
Down near the bottom of the chat.
Oh, I don't know what that dark band of rocks is in the middle of the rock cut. I'll look for it next time I go.
Okay.
It's possibly, there's a number of possible explanations. If it's horizontal, it could be another sedimentary layer that just has an unusually high amount of organic content in it. So kind of like shaly. And those shaly bands tend to be aquifers within the limestone sequence, so they're often wet, which makes them darker. So that could be a possible explanation. There are a few intrusive rocks that are present in the Kingston area, but very few of them young enough to be intruding the limestones. So I'm going to have a look at that next time I'm out there. So that's the Berryfield rock cut, right?
Yeah.
Okay. Thanks for that.
We've got someone, Mike is asking about there's a marble quarry property near Marmara, sorry, with granite whalebacks, marble, and diabase dikes / sills. And Mike's asking about the relative ages of these different features.
Well, we can turn you into a geologist, Mike. There's the law of sort of temporal superposition. So if the diabase dikes and sills cut across the marble or the granite whalebacks, then they're younger. I would suspect that the oldest rock of those three is the marble. It was probably intruded by the granite. Although if the granite intruded early enough in the mountain building process, it would in fact be deformed itself by tectonic forces. But the diabase dikes and sills are almost always going to be the youngest of the three. Yeah, but it merits a trip. Merits a trip.
The last thing I've got in chat is just a comment. Steve and Manders has said that Gould Lake was called Cold Lake in 1860 because the prevailing winds blow the warm surface water to the north end, drawing up the cold deep water at the south end. The map maker must have heard the name as Gould Lake through a Scottish accent. And,
Entirely believable. Good story.
Yeah.
Yeah.
All right. Well,
I'm going to stop sharing.
That was really interesting. Thank you so much. Maybe we can move on to the photo sharing for that. And now it's time for the draw. I think I have to stop sharing screen now. Is that right, Mark?
Yeah, that's correct.
Do that. There we go. And see if Mark has sent me a list. He has. Excellent.
You want to know anything about the club?
Yes, that would be great if you could tell us about the club, and Mark and I will sort of get set up to do the draw.
Okay. I'll keep him busy while you do this in the background. So the Kingston Lapidary and Mineral Club has very generously donated a family membership for 1 year to the winner of this draw. The club is at the Tet Center. It's got several hundred members now, and it's a club that originally started decades ago to go. It was a bunch of rock hounding enthusiasts and rock polishing enthusiasts that got together and formed a club. And so lapidary is rock polishing, and the mineral part refers to the rock hounding bit. But now it's a club that does three things. And in fact, the third thing that it does is probably where most people spend their time, and that's doing metalsmithing, working with silver, brass, and copper, and most people make jewelry. And you get the occasional person who is such a devotee that they will actually go hunting, say north of Kingston, find some beautiful crystals or a rock with some crystals. They'll come back to the club, cut the rock open, liberate the crystal, polish it up, and then they will set it in silver and make a ring out of it, something like that. And anyway, it's a fun club. They are always organizing group field trips to go rock hounding. So if tromping around in quarries or in the bush appeals, then this might be something for you. Did I
Mark,
talk
are
long
you
enough?
set? Mark, have you got a random number
Sure,
generator?
yeah, so I'll give you the number and it should correspond to a row on the
Alrighty.
I sent. Okay, so the number I have is 84.
84. Okay, that's Lynn Brown. Lynn, are you with us?
Yeah, yes, I'm here.
Oh, great. First time. That's great. Well, you are the winner of the draw. So as we close down, just hang on so we can get your contact information because David's going to need to get some contact info so he can set this up for you.
So wonderful. I'm so excited. Thank you.
Great. Well, I guess that wraps up our event. So really appreciate everyone coming. I'm glad that the power held out for us. And thank you again, David. That was really, really interesting. I really found that fascinating, actually. So thank you very much. And maybe we'll see you at our next webinar. Good night, everyone.
Thank you.